is our lesson number 24, Discrete Probability Models, day 1. All right, in order to understand discrete probability models from section 7.1 of the book, we're just going to start off with random variables and sort of go through there. So basically, this is a review of your MA 206, sort of a couple lessons, maybe 2 or 3 lessons in MA 206. So what is a random variable? We're going to let that be a function that assigns one and only one number each outcome in a sample. So I'm going to go ahead, make this one big giant long line, and then give you some of the. So the way that I'm going to write a random variable, like if it was a random variable x, I'm going to put these little above and below lines on there to let you know that there's a capital X, because in general, the way that folks write random variables is with a capital letter. And then later on, we're going to see where the small letters come in. Or if it was a Y, we're going to see a Y here in a few minutes. This is a capital Y. We all remember that the sample space has this funny little S on there, and so maybe it looks something like that. So that's what a random variable is. After you understand that, well, then the next part is to go, so what is the support? So the support for distribution is, and let me move this up here. So a support / domain of a random variable. That's simply all of the numbers that can be assigned in other words, all of the, so it's the domain for the distribution, support for the random variable. What we're talking about are all the numbers that can be associated with it. So for example, or just to recall that these can be, so can, let me get a little pen out. So again, I'm not perfect at this yet. So it can be discrete or continuous. So these can be discrete or continuous depending on sort of the problem. Depending on the problem. And today's lesson, we're really talking about discrete, right? So that's what we're going to be focused on today. And then later on, we'll come back and we'll continue. We'll look at these continuous ones. Okay, and here's an example. So, I mean, again, we're going through the definitions here, but we're going to see an example of what a random variable is. And then I'm going to give you a couple of different random variables for a particular experiment. And then we'll come back and we'll find out what the support is for each one of those and see where the support comes into play. Okay, so suppose, oh, here's the experiment right here. So our experiment is we're going to roll 2 4-sided die. Note that this is a 4, not a 6-sided die. Maybe a red one. I'll just underline this as red. So I got a red die and I have a green die, right? So they're going to come up with the numbers. First thing is we want to do is figure out what my sample space is going to be for this experiment. And that's pretty straightforward. I can have a 1 on a red die and a 1 on a green die. I can have a 1, 2. I can have a 1, 3. And this is pretty standard for figuring out what the sample space is, to go through all of, so start with 1 and then go through all the greens and then increment the red and then go through all the greens and increment the red and go through all, you'll see. So I increment the red and say it can be a 2, and then go through all the greens that we could have possible. So 2, 2, 2, 3, 2, 4, 3, 1. Okay, so everyone sees what we're doing here. And I'm just going to write them out for completeness. We'll come back and look at some of these here in a few minutes. But you can see why I decided to make it a 4-sided die, not a 6-sided die, because my sample space would have been a lot larger, right? So 6 times 6 is 36 numbers instead of just 4 times 4, which is 16. Okay, so that's the sample space. I'm going to give you an example of 2 different random variables. One that you're probably sort of thinking about what's going to happen here, right? So the first one would be the random variable x for this particular experiment. Again, draw those little lines above and below, and I'm going to define this random variable as the sum. So the sum of the numbers that appear, the numbers that are on the face. In other words, the face of the die. For example, whatever your red die is plus whatever your green die is. So an example would be, what would 1, 3 be? So if this were 1 were a red and the 3 was the value that's on the green die, what would we come up with? Well, 1 plus 3 is equal to 4. So this is, so if we go back to the definition, we see that a random variable that assigns one and only number to each outcome. So the outcome here that we're talking about is 1, 3. So that's the one I'm interested in. And the question is, well, what number do I assign to it? Well, the answer is 4, right? So so for the outcome 1, 3, where 1 is on the red die and 3 is on the green, I'm going to come up with a 4. Let's define another random variable. And this one we won't really go that far with, but I just want to show you that you can have a different random variable for each one of these suckers. I'm sorry, for each experiment, you can have a different random variable. So we can have it a y, and we can say, well, y is the difference. Instead of being the sum is what we're probably used to. Let's just let it be the difference between the red and green die. Okay, so R minus G. So we got the difference between the two. So what is y of 1, 3? So again, it assigns a specific number to the outcome. So if this were the outcome of my experiment, we would expect this to be 1 minus 3 is equal to negative 2. Now let's talk about the support. So what's the support for x? So the support for x is numbers between, well, what's my smallest number I can have is 2, and my largest number is 8. Support for y is, let's see, what is the small, let's say a 1 and a 4 would be a negative 3. I think that's the smallest one. Let's see, 2 and a 4, yeah, and then 4 and a 1 probably. So it's negative 3 to 3. Negative 3 to 3 inclusive. That's what I think it is. I mean, you can go through and see that. I think that's the smallest number you'll get. Anyway, so that's the idea of the support for a distribution. The support for this random variable is what values, what numbers can we possibly get in the experiment. So our next step, after we sort of figure all that out, is, okay, well, I need to know what the probability mass function is, right? Because now we're going to start assigning probabilities. And the way we do that is we're going to let this be, this is not a capital X anymore, it's a small x. And the probability statement that we write here is the probability that the random variable x, right, capital, is equal to some small x, which is this guy, is equal to p of x. So this becomes p of x. Right, and then up here is the support for the distribution, right? So all of the x values that I could possibly get, I'm going to go ahead and put up here. All right, and so I have a 2. We can get a 3. Hopefully I got enough room here. 6. Hey, looks like I must have calculated it out. So I get 2, 3, 4, 5, 6, 7, 8. And then the probability of getting that. So that's the next question. Well, I think this one is 1 over 16. Now you might ask yourself, why in the world did I put 1 over 16? Well, we have an assumption that we didn't say here, right? So I could probably type the assumption in here. My assumption is, think about it for a second, and it's probably that we have a fair die. Fair die. And let me move this around. So I don't know, where should we put this? Maybe right here, right before we start writing in the probability mass function. Now, why do I need that for an assumption? Because I need to start assigning probabilities. The question is, well, how many different things can happen? If I have a fair die, then I have an equal probability of each one of these outcomes occurring. And we start to multiply, right? So I got 4 plus 4 plus 4 plus 4, or 4 times 4. So there are 16 total outcomes. So 16 outcomes, right? And then how many of those 16 outcomes do I get a 2? Would be your first question, right? Because that's what we're talking about here. Well, if you go back and look at it, this is the only one that has a 2. So we'll start keeping track. So I have 2. All right, and then we'll go down the line here. How many 3s can I have, right? So I got a 3 here and a 3 here. So it looks like maybe there's only 2 of them. Keep going down the line. Oop, I tell you what, let me go here and choose that orange color again, because I already have a 4 there. 2 and 2 is a 4, so that becomes a 4 there. And 3 and 1 becomes a 4. I think that's all we have there, so there's 3 of those. And then we'll do one more, 5s. So I have a 5. 2 and a 3 is a 5. A 3 and a 2 is a 5. And a 4 and a 1 is a 5. So we have 4 of those. Okay, so if you start just doing the calculations or the math here, you start seeing that this is pretty straightforward. So I have 2 over 16 for 3s. If you go back and start counting them up, I have 3 over 16 for 4s. I have 4 over 16 for 5s. Let me move this a little bit. And we have 3 of these. So it starts going back down after 5, because there's 5 in each one of them. And then only 2 7s and only 1 8. And so if we recall from our probability classes, if I have all of the numbers I could possibly have here for the support, then these probabilities have to add up to 1. In other words, one of these, it's 8, 7 numbers. One of these 7 numbers must occur in order for us to have the entire support for the distribution. So if one of these has to occur, then my probability has to add up to 1. I can't have anything else occur. That's the probability mass. So basically what we're doing is we're taking a mass of probability and spreading that thing through different values for the support. So the next question is, what is my cumulative distribution function? And the reason why we have that is it does, sometimes it's easier to calculate probabilities of a whole bunch of things all at the same time. And yeah, that was a really bad P. But that is probability that x instead of equal is going to be less than or equal to x. And that's going to equal to capital F. And when we get to continuous, we'll remember, unless you remember already, why we use a capital F here and a small p there. So So let me write f x here, and then we'll just start doing the calculations, right? So the probability that I'm less than or equal to 2, well, that can only occur if I got a 2. So that's obviously just a 1 over 16. Less than or equal to 3, well, it's all of the previous accumulations plus whatever's in here. So 1 plus 2 is 3/16. The probability that I'm less than or equal to 4 is all of the previous accumulations, which is this number here that's in the CDF for 3 plus the one for 4. So I get 6 over 16. So 3 plus 3 is 6. Here, 4 plus 6 is 10. And we just continue this. 13/16. Because it's all of these added up together. 2 is 15/16. And 1. I could write 16 over 16, but it's all of the CDFs end with 1. So this is my support. This is my probability mass. This is how I distribute out my probability mass. This is called the cumulative distribution function, because a lot of times it's easy to answer questions about if my support is really large, I want to use the cumulative distribution function. So let's go and see what that looks like. So if I'm scrolling over here, this first one that I want to put up, and let me add a text. So I'm going to call this, move it up, EMF stands for probability. All right. And then, well, what was the first one? We can scroll over, but if you remember correctly, that it's just, this is where the support goes on this picture. So 2, 3, 4, 5, 6, 7, 8. It looks like I have an extra one of those guys, but it doesn't matter because I just won't put anything on it. So maybe I had this as 1. That's probably what it was. I probably wanted to make that 8 and let that be 1, but nobody cares. We'll draw this sucker in. So if you remember, the probability that I was 2, the amount of mass that's set here was just (1)16. This is 2/16, 3/16, and 4/16. So yes, this is supposed to be a bar. All right, and then what is the 2? Well, it just has this bar, and I'm not going to fill it in. Probably made it look worse by filling. And I have these yellow lines here just to help me out. 4 was 3/16. Because I cannot draw very well on this. And yes, that is supposed to be a rectangle. And then it's going to get even worse here for 5 because it's way up at the top. I'm going to try to stay, if I'll go slower, maybe I can make this into a rectangle. It's a horrible rectangle. All right. And then this one comes back here, but you get the picture. You get the idea, hopefully. And then this one's 2. And this one's 1. Okay, so that's what the picture looks like, in sort of. Yeah, I know these are not great bars, but there's the best I can do in this little tablet here. So that's the probability mass function. That's sort of what it looks like. And then we got the cumulative distribution function. And I'm just going to write this sucker in. So this will be the CDF, the cumulative distribution function. And this will be the support 1, 2, 3, 4, 5, 6, 7, 8. So this is 1, 2, 3, 4, 5, 6, 7, 8. So what, and I'll draw it in red. We'll make it blue. So what happens is for the cumulative distribution function, it's 0 everywhere up until this point. At that point, it goes up to 1/16. And then it stays at 1/16 until it comes to here, and then it goes up 2/16, which is 1, 2. So it goes up to here. It's supposed to be a straight line, like a step function. And it comes over here to 4, and then it goes up 3. So it goes from here, 1, 2, 3. This one goes up 4, 1, 2, 3, 4. And it comes over, it goes up 3 again, 1, 2, 3. It comes over to 7, it goes up 2, 1, 2. I think it's right. Let's see. I think I'm right here. I'm supposed to be right there. Oops. 7 goes up to, it should be go up to about right there. And then finally at 1 it goes up, or 8 it goes up to 1, and it stays at 1 forever. Okay. So this thing actually comes from negative infinity all the way, stays at 0, and kind of works its way up. Where these little jumps here are the probability masses. So 4 was, I believe, 3/16. So this distance here should be 3/16. Distance here should be 4/16. This distance should be 3/16. And so on and so forth. So that's what they look like. Okay, that's the sort of the first step in understanding what a discrete distribution or discrete probability models look like. The next thing we want to do is we're going to start looking at expected values. In order to do that, I'm going to go ahead and introduce a new problem, and then we'll try to figure out if we can figure out the expected value, what that is. Again, this is review, and this is a couple of different lessons in MA206, so just sort of roll along here. Okay, so the example 2 is, suppose we know the true distribution of flash drives sold in a store. In the true distribution, and I'm going to draw this sucker out. So the true distribution is this one. Move it up. So yes, I'm drawing this one in blue, looks like. So I'm letting this be X. And what we're saying is these flash drives can only be sold in 1 gigabyte and 2 gigabyte. And 4 gigabytes and 8 and 16. All right, and we haven't defined our random variable yet, so let's go ahead and do that. We're going to let X be the amount of memory for a purchased flash drive. And then this will be our probability mass function. What we're saying is we know what the true value is, and we're going to say this is 5% of the time people buy 1 gigabyte, 10% of the time they buy 2, 35% of the time they buy 4, 40% of the time they're going to buy, yes, and that is a 4. And then 10% of the time they're going to buy 16. So it looks something like this. This is P of X. And these are the probabilities that go along with that. And so the real question is down here. what is the long run average of the long run average size of a purchase flash drive? So that's the question. If you think about it, I think it's pretty intuitive that if these are the true percentages of a 1 gigabyte, a 2 gigabyte, and so on and so forth, if we're looking for the long-term average, then if these are true, then it's just simply a weighted average between these two. And the notation that's used is the expected value of the random variable x, where we called this our random variable, the amount of memory for a purchase flash drive, is simply going to equal to mu, which is also referred to as the mean. And it's going to be equal to that weighted average that we just talked about. So it's 5% of the time we're going to purchase 1, and 10% of the time we're going to purchase 2, and 35% of the time 4, and 40% of the time, so decimal, we're going to purchase 8. Then 10% of the time we're going to purchase 16. So if we simply just add these guys up, we would get 6.45 gigabytes. Now, what is that saying? Even though we can't, I mean, there's no way I could go into a store and purchase one that's 6.45 gigabytes, because the only choices that we have are 1, 2, 4, 8, and 16. What we're saying is, if you took in the long term, in the long run, that's what we're talking about with the expected value. Is if I just listed all of the ones that were purchased to infinity, as many that we could add up and divide by the total number, we would get an average of 6.45. So that's the idea behind that. So what is the formula for this? Given any, I mean, I know we did it for this particular example, but the formula for the expected value is simply set back to value for some random variable is simply the summation sign, which just means add a whole bunch of them up over your entire support of x. So the number, right? So that's where we get the x, the 1, the 2, the 4, each one of those suckers, times probability of x. So this is also equal to the true, that's a horrible mu. Let me erase that and start over. This is also equal to mu. Yeah, another horrible mu, but we'll have to live with that one. All right. So the mean, sometimes you'll hear the mean of a distribution. Sometimes you hear expected value of the random variable, but they all mean the same thing. The true mean, not the sample mean. All right. Another thing that we're concerned with, it's not just the expected value. Oh, hold on. Let's talk about where the expected value, what it looks like. So let me come back up here. So what you're doing, we can't do it there. What you're doing is you're finding the middle of this distribution. So I was going to show you on the example that we had already done, but what you're trying to do is you're trying to find what the expected value is, the middle of the distribution. So if I was going to put the probability mass, some of it over here and half of it over here, we would be looking for the part where it sort of balanced out. So if we had a plate and we put this one at position 1 and 5% of it at position 1, 10% of it at position 2, 35 of my mass at position 4, 0.4 at position 8, and 0.1 at 16, then the place where we can balance this out would be at 6.45. So that's what we're talking about with we're trying to find the middle of the distribution. Another thing that we might be concerned with was how spread out is this distribution. So sometimes if this were 1 and this were 1600, well, this distribution would be very spread out, much more so than it is now. If this was 0.1, 0.2, 0.4, 0.8, then this distribution would be sort of squeezed in maybe a little bit more. So the idea here is that how can we go about and get a measure for how spread out a distribution is? So all we're going to use is the variance. And let's define what the variance is. It's simply just how spread out. Let's do it for this example. So what am I going to do? For each one of these numbers, like for example, 1, how far away is 1 from 6.45? How far away is 2 from 6.45? How far away is 4 from 6.45? And then multiply that by the amount of times that should occur. So if this were higher, then we would want the 1 minus the difference between 1 and 6.45 to count for more. But since this is small, then it's okay for it to only be 5%. So that's the idea, is that we simply go, how was the spread or the amount of variance in this distribution, or how spread apart is it? We're just going to take 1 minus 6.45. And the problem here is I don't want it to, let's go back up here real quick and look. I don't want this I don't want it to cancel out. So this would be a negative number. And then when I get on the other side of 6.45, I would be positive. And so I don't want that to cancel out. So what we're going to do is squared. So we squared and then times the probability, because that's the percentage of time, the percentage of the time that occurs, and then plus 2 minus 6.45 squared times 10% of the time plus 4 minus 6.45 squared times 0.35 plus, what is it, 8 minus 6.45 squared times 40% of the time, and then finally 16 times 0.1. And this would give us an idea of how spread out the distributions are. So how far away from the mean are you? And if you did this calculation, you would come up with 15.6475. So that's what the variance for this particular one is. But what is the formula for it? So again, it's kind of this idea of, well, regardless of the distribution, I want to sum over the entire support. Instead of x, this time I'm going to put x minus mu squared times p of x. How's the probability of that? So this is our formula for variance. Okay. Now what we're going to do is going to go ahead and go to R, and we're going to calculate or do some of these things. I'm going to show you how to do this. I do have a meeting that's scheduled, so I'm going to stop right now, and I'm going to come back and do this later. So let's go to R and figure out how to do this in technology. So bring up R, and we're sharing, bring in a script. And then what we want to do is basically reproduce what we did by hand here, right? So I'm going to call this support. I could call it X. Let's call it X. All X is equal to C of 1, 2, 4, 8, and 16. And then the PMF, the probability mass function, is we're just going to put in the probabilities that we had for this one. 5%, and then and our CDF. So if you highlight these three, see, make sure everything's correct. And it looks like everything came out right. All right. The next thing you want to do is look up a bar chart. I'm not sure how to do that, so I'm going to share my Google machine with you. And so let's go to Google. Let's look up bar plot in R. And so if you go to bar plot in R, it looks like you put in the counts, and then we can label. It probably has the numbers here. Names.argue. Okay, so it looks like if we put in this names.argue argument, then it might work for us. So bar plot is the thing. This will be, as for us, it'll be PMF, and then we'll put this as X. So let's stop sharing this. Go back to our R notebook. Type in bar. Let's see our probability map. And then maybe names.arg, I believe is the name. Yeah, there it is. There, and it looks like if you look over here that we get sort of what we're looking for, right? So that's the probability map. Go ahead and put it in there. I think it's called main here. So let's say main is equal to PMF. The math. All right, so that's what we got there. Let's see if we can do the CEF. I looked this up before. I think the step function is we just got to tell it what type we want. So we're going to plot. Let's see, we need to start it. I need to put the CEF there. No, we'll put an X in there. And then what I want to do is go to the end of X. So the way we do that is tail of X, comma 1. I don't know. So that will be what's happening here is I'm starting at 0. That's where I want the CDF to start. And then I want it to go up by increments at these particular spots. And then I want it to go past it, right? So I don't want it just to stop at the last X. I want it to go a little bit past it. That's why I added 2 to it. And then we're going to do the same thing here. I got to tell it to start at, I don't know, 0. We could put some other, this one's definitely 0. So this one could be possibly be negative. I mean, maybe I could put -5 in there. We'll see what happens. It's definitely 0. I want the Y to start at 0. And I want the Y part that goes by the CF. And then I want it to go up to, I think the most, definitely 1. And then type. Okay, so it looks like that's what we're getting. So again, I put this -5 in here because it's really to negative infinity. So it's coming in the first part, and it gets to is 1, and it jumps up 0.05, and it goes over to 2, and it jumps up 0.1, and then it goes over to 4, and it jumps up by, let's see, 0.35. I think this is 0.35 here. And then it goes over to 8 and jumps up another 0.4, and then it only has 0.1 there again. Okay, so that's the CDF. What would this look like if I was going to try to calculate the expected value? Let's just calculate it. We'll say it's the sum, because that's what the big sigma stands for. Support. That's not support, it's X. I'm used to using support here for that, but we can just use the X. X times the PMF. See what we get there. 6.45 is which we said before. And then if I was going to get the variance, I would say sum of X U equals. Then we're going to have X giving us what we think. So this would be all right. So the next thing that we possibly want to do is check out. Let's put it in a data frame so we can see it all. So this is capital X for the random variable, and we'll put everything into a data.frame. Maybe my entire X, my small x is equal to then my PMF. All right, so you look down here and you get when x is 1. So this is sort of on the side. If you think about what we did before, we had the 1, 2, 3, 4, 8 coming across the top, and then these numbers were the second row, and this number was. So let's see. Yeah, so this looks like a little bit what we've seen before earlier in the thing, right? So I have a 1 here for the small x, and the PMF for that one's 0.05, and the CF's 0.05. And keep sort of going along, and it looks a lot like we had before. Okay. How would we get probabilities out of this? Okay, so probability capital X, and then we're going to set small x equal to, oh, we've already put it in there, so we're good. We'll set it equal to some number, one of the ones that are in there, let's say 4. And so this is coming down here. So if I'm looking to get this number out of my data frame, so go X $PMF, and then bracket, and then there's this function called which that will look things up. Which X is equal to. This says which one of these things is equal to whatever we set this guy equal to. Didn't like that at all. Oh, it's 2 equals. So it's a double equal sign there. We get 0.35, which is that what we expected. For 4, it is. And if I wanted to find the CF, so a couple ways we could do it, but if we're going to use this way, I would simply copy this, paste it, and change this to. Okay. And that's all I'm going to do in R. So I'm going to go ahead and stop sharing R. I'm going to go back to our whiteboard. So we've seen this number in R. We've seen this number. It's not very good writing, but we've seen this number also in R. So now what we want to do is get some rules for expected value, right? So we want to go and change. So I'm going to put this in red because this is a sort of a little different topic than what we've done here. When I say different topic, I mean this is, we're kind of expounding upon what we've already done. So what I'm looking for is the expected value. Let me move and get my pen up over here. So I'm looking for the expected value. What I would like is the expected value of some constant times a random variable plus some constant. So we want to know what that is. So let's just use our definition. So look at what we did here. So I expected value of X. All I did was I took whatever the random variable was and I turned it into every single one of them. So I used a small x over here, and then I multiplied by P of X over the entire support. So that's what we're going to do in this case. Go back here. I'm going to have the sum of X inside the parentheses A X plus B, right? So I changed this from a capital X to a small x because I'm summing over the entire support, and then I got to multiply that by, just like we did here, I got to multiply it by the PMF. that is equal to, right? So now I'm just going to use some laws that we already know, some things about summation signs, some things about distribution. So I'm going to then simply just distribute the summation and the p of x. And so I know that this is equal to the same thing as a x, put this in parentheses, times p of x plus the sum of x times b times p of x. All right, let me move this up a little bit. And then this is equal to, okay, so for a summation sign, if I'm summing over all x's and I have a constant here, I can pull this bad boy out. So that's what I'm going to end up doing here, is pulling that out of the summation sign. And then we notice, hopefully we notice something that's familiar to us, x times p of x. And then I'm going to do the same thing with this one. I'm going to pull out a b because it's a constant, and then I'm left with p of x. Okay, so what do we notice about this is that it's equal to the expected value of x. Right, it's exactly this definition that we used up here for e of x. So this is what's inside here. And so I'm just going to replace that with the expected value of x. And then we should know, if I sum of all the probabilities in the support of x, then we know that this is going to be equal to 1. Because if I sum up all these probabilities, then we better get 1. And so this whole thing is going to be a times the expected value x plus b, which is what we were looking for. So it becomes a linear operator. Sorry, so I can take this e inside here, distribute it, pull out constants, and I can pull out a constant, and you just pull the constant out and multiply by expected value. So if I have some linear function that I'm trying to take the expected value of, then that means I can just take it inside. All right, so that's one result that we're looking for the expected value. And next, what we want to do is do the same, at least look at the same thing for the variance and see what happens to it. So the variance of a x plus b is equal to, treat it as a linear operator as well. So it is the variance of a x plus the variance of b, which is equal to, so we're going to take this thing and turn it into, let's go back up real quick. We're going to turn it into here, right? So all I'm going to do is everywhere I see an x, I'm going to take a times x minus mu, or, yeah. So it just becomes sum over x a times x minus mu tell you what, we're going to do it a little different way. I'm going to put a x minus a mu quantity squared times p of x plus, right, so this part, this goes with this new quantity here. We just replace the x with the minus mu. And now here, quantity squared times p of x. So this guy turns into 0. So this whole thing is 0. And we're just left with this. So we're going to bring that down. The sum over x. And I'm going to go ahead and multiply this guy. So I get a squared x squared minus 2 a squared x mu, right? When I multiply those, I get 2 of those, and then I get plus a squared mu squared. All of this times p of x. All right, I need to move this up a little bit. All right, so what is this equal to? Sum over x of, so I can notice I get a squared, a squared, a squared. So I'm going to bring an a squared to the outside of the summation sign. And then we're just left with x squared minus 2x mu plus mu squared p of x, which is equal to a squared summation over x minus mu quantity squared p of x. And what is this guy? I guess I should have put that in another color. This is just the definition of variance. So we're going to just call this what it is. So it's equal to a squared variance of x. So look what happened. Here, when I took the variance in, all I do, if I want to find them with the variances of this linear function here, is that everywhere I see, if there's an x involved, then the random variable involved, I pull out the constants out and I square them. And then it just becomes the variance of that random variable. Then plus, if I have just a constant by itself, then the variance of a constant is just 0. I mean, if you had b, 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 there would be no variance. It would always be b, and so there is no distribution of that. All right, and then the last thing that I want to do is what's called a shortcut formula. I'm not sure, I may have already put that in here. So shortcut formula for variance. Pretty important. It might not look like a shortcut formula for now, but believe me, in a few, when we go to do some of these distributions, you're going to need this little shortcut formula because it'll turn out to be a lot easier. All right, so the shortcut formula starts off with simply just saying the variance of x. So we're just going to start off with the definition, or with how we defined it. And it's the sum of x mu minus x. I don't like that. You could do it this way. I just don't like that. I like going the other way. X minus mu. I don't know why. It's my preference. It doesn't matter because we're squaring it anyway. Times p of x, which is equal to, so we're just going to go ahead and square this stuff. So it looks a lot like it did above. So it's x squared minus 2x mu plus mu squared p of x, which is equal to, so now all we're going to do is bring this, again, a bunch of distribution, and using the fact that I can sum these whenever I want to. So it becomes the sum of x squared, and bringing the p of x in. and then minus. So here I'm bringing out this constant mu, because it doesn't have an x in it. Oh, there's two of them. 2 mu. So let me just go ahead and fix all that. It looks like garbage. So minus 2 mu summation of x times p of x plus u squared sum of p of x. And we know already that's 1. We've already talked about that. So it just leaves me mu squared here. We know this is another way of saying mu. Go back up in your notes up top and you can see that. So this is expected value of x or just mu. And this is just this we recognize as the expected value of x squared. So if we've defined the expected value of x, I don't want to select that. If we define this expected value of x as x times p of x, then the expected value of x squared is the sum over x of x squared times p of x. So we're using that definition of expected value and going in reverse here. So we're letting this be the expected value of x squared minus 2 mu squared plus u squared is equal to expected value of x squared minus this piece right here ends up being minus mu squared. But another way of saying this is minus expected value of x quantity squared, so the whole thing squared. Okay, that is your shortcut formula. So if you've ever calculated the expected value and you're trying to find the variance, which you're going to have to anyway, even if you're using this one, then you might as well just square the term and just find the expected value of x squared. Now, what does that look like? What is the expected value of x squared? Well, let's find this. Oh, it looks like let's cut that. Let's delete that. All right. So let's actually do this on the distribution that we've already been given in the example problem up here. So what we want to do now, I'm going to do it in a different color. I'll do it in green. I want to find the expected value of x squared, just so you've seen this before. So it's just 1 squared, right? Because all I'm doing is I'm taking this and then I'm multiplying it by the probability times 0.05 plus 2 squared times 0.1 plus 4 squared times 0.35 plus 8 squared times 0.4 and plus 16 squared times 0.1. And we can come up with that number. I'll use R here to find that number. And then we can subtract 6.45 squared. And then we'll get, hopefully, the exact same number, 15.6475. So let's use R to figure that out, to make sure that it gives us what we think it should be giving us. And then hopefully we prove it to ourselves. So we'll stop sharing this. We can go to R. And put this over. So in R, we want to sum x squared times times PMF, and then we want to subtract 0.45 squared. Ooh, that's not good. Oh, that's because I used 4 here, right? So I got to go back up here, just Control Enter again, and then do it again, and we got 15. So I redefined what X was here. So all I did was I went back up here, reran this, and then found that, right? And so we get the same number as we did earlier when we said the variance. So we get the same exact numbers. All right, well, that's all we got. We will continue this discrete probability. Probably next video we'll talk about the binomial distribution, because I think you need that in order to solve a couple of problems, or maybe just the Bernoulli. Anyway, we'll go through Bernoulli and then binomial, and we're going to use some of these concepts that we talked about in this particular class in order to be able to do those.